The most advanced optical systems in data centers deliberately place their laser sources as far away as possible from the chips they are supposed to power. And this counterintuitive design choice is the breakthrough that finally made co-packaged optics work. Welcome to the channel. My name is Vikram Shekhar, and I write a Substack called Vik's Newsletter, in which I discuss a whole lot of stuff about semiconductors. In this video, I'll discuss why the industry decided to put lasers external to the co-packaged optics or CPO system, and why the temperature dependence and the sensitivity of a laser's wavelength is such a big factor on the laser threshold and the efficiency and its eventual lifetime. Okay, let's talk about laser sources. Why do we need laser sources to begin with? We need them so that electrical information can be converted into the optical domain, into light. And the way this is done in today's optical transceiver is to integrate the entire transmitter and receiver section into what is called a small form factor pluggable module or SFP module that plugs right into the front of the switch on the rack. Let's look at what the internals of an optical SFP transceiver looks like. There is a transmitter optical subassembly that consists of a driver IC, and it drives basically a laser diode. So electrical signals can be converted into optical signals through the transmit path. Similarly, there's a receive path consisting of the receiver optical subassembly that involves a photodetector and a transimpedance amplifier that amplifies the signals. Now, there are a few things to note here. One, the complexity of this assembly on a PCB is quite high. And secondly, if anything on this pluggable module fails, it can simply be taken out and replaced with another one. When we're talking about CPO, this becomes a difficult problem because in CPO, this entire optical transceiver that was outside the rack is almost entirely integrated into a silicon photonics switch that is sitting right next to the switch ASIC. But if you notice this picture, there is a distinct choice being made to put the laser, even in the CPO system, outside the rack module. This choice is intentional, and we'll get into more of why that is the case. To understand why lasers are sensitive to temperature, we need to understand how laser action works. Laser action almost entirely occurs only in 3-5 compound semiconductors because they have what is called a band gap. I have a whole article on why we need a band gap to generate laser action and why silicon having an indirect band gap is very difficult to build lasers on. If you look at the direct band gap material, there is an energy band gap or EG that separates the valence electrons in the blue from the conduction electrons in the orange. Whenever electrons transition from the conduction band to the valence band, they give off energy in the form of light. So this is why laser action even occurs. This does not happen in an indirect material like silicon because it also needs a vibration wave called a phonon. We won't get into it here. When the temperature is raised, this energy band gap gets smaller because the electrons get a lot more energy from their external source. And so when the energy band gap gets smaller, the energy of the laser photon emitted from the transition also decreases, which means that the laser wavelength goes to a higher value. You can think of this as a red shift. Any laser operating at room temperature gets shifted to the red side of the spectrum when temperature is increased. This is a big deal because, as we will see, we want to put a lot of wavelengths right next to each other to do something called wavelength division multiplexing. The impact of temperature can really upset how many channels we can send together in an optical fiber. The next problem is the impact of temperature on lasing threshold, which is another way of saying how much current is required before the lasers can start operating and generating light. And the efficiency, which means how much input power is required for some amount of optical power to be available. This figure shows an indium phosphide distributed feedback laser from Lumentum, and you can see clearly here that the current increases for a same level of output power when the temperature of the laser diode is increased. And here on the right side, you see all the laser wavelengths shift towards the red end of the spectrum as its temperature is increased. And of course, if you increase the ambient temperature, which is basically the case temperature, the efficiency drops. And the efficiency is already like only 10%. And that's really means that 90% of all this energy is burned away. So we really want to keep laser efficiency as high as possible. Finally, we have the impact of temperature on lifetime. When you take a laser operating at 25 Celsius, and let's say that it operates for a total of 10 years, if you increase the laser temperature to operate at 85 degrees consistently, you can expect that its lifetime drops by a factor of 10. That's how significant temperature is to the lifetime of lasers. So, for all this, the industry came up with one simple solution. Don't put lasers where there's a lot of heat. Now, co-packaging a laser right next to the ASIC switch that is dissipating hundreds of watts of power is a bad idea. It's like putting an ice sculpture next to a blazing inferno. You just don't want to do that. So what if you just take the laser and put it entirely external to the rack? And this is what is the current solution deployed in co-packaged optics today. In the Substack, we discuss a lot more about laser failure rates and how the serviceability problem is solved in CPO. What kinds of lasers are used in CPO, some reliability numbers, and who the major players are. Again, for more details, check out the link in the description below. And if you haven't already, click subscribe on this video for more detailed discussions on semiconductors like this one. Thank you for watching.